Hello everyone, welcome back to Electronics 1. Today we're going to look at analyzing a circuit with our ideal diode models through the use of an example. Okay, so for this example we'll have a circuit with two diodes connected to two resistors, and connected to ground and two power supplies. This supply being plus 10 volts, this one minus 10 volts, this R2, this one R1. Let's call this, let's just label this D1, and let's label this D2, and let's label oops, let's label output voltage V out at this point, which is what we want to solve for. Okay, let me copy this because I'm going to use this again and in another iteration of this circuit. Okay, let me put a value on my resistors here. Let's call this, let's assume this is a 10K resistor and that this is a 5K resistor. And let me label some voltages and some currents here. So I'm going to call the current down through diode 1, I'm going to call that ID1, and I'm going to call the current through diode 2, let's call this ID2. Okay, and I'm going to label this node right here as Vx, and I'm going to label the current here in this point in the circuit, let's call this Ix. Okay, so the circuit is sufficiently complex that it's not obvious whether our diodes are conducting or not, or on or not. So to analyze a circuit like this, we have to make an assumption, an educated guess, whatever you want to call it, and work from there to determine whether it makes sense or not. Okay, so for this case, let's assume diode D1 and D2 are both conducting. Okay, or in other words, let's say they're both on. Okay, so if the diodes are both on, right, they would both appear as a short circuit, right? So I'll just replace them with a short circuit as like shown in the pink here. And if that is the case, then this point here, which is ground, well, that ground is going to extend to here and to here and to here, right? Because if those diodes are on and shorted in the ideal case, then that voltage is the same everywhere along kind of where I've circled, where I've colored in green here. Okay, so based on that, I could calculate the current through diode D2, right? Because if this voltage here is 0 and I've got 10 volts at the other side of this resistor, well, I can calculate the current through that resistor. That's the same current as through diode D2. So current through D2 is going to be equal to the 10 volt voltage drop across R1. We could look at it as 10 volt minus 0, but let's let's call this VR1 minus, or divided by the resistor R1. Okay, so we've got a drop of 10 volts across R1. Let me put in the value for R1 here, 10K. So this suggests that my current through D2 is 1 milliamp. Okay. Let me solve for this current, Ix. I can do this the same way. I can calculate the voltage across R2. Okay, so I want to know this voltage VR2 here. Okay, so, and that'll allow me to calculate the current through R2. So Ix is going to be the voltage across VR2 divided by R2. This is 0 volts minus a minus 10 volts divided by 5K, which is 2 milliamps. Okay, I can, to solve for current ID1 here, I can perform KCL at this node. Okay, so current in should be equal to current out. So KCL at node X, I guess I'm calling this node here X. At node X says that the current in must be equal to the current out. So the current in is ID1 plus ID2 is equal to Ix. Okay, I've already have ID1 or ID2 and Ix, so I can rearrange to solve for ID1. It's going to be Ix minus ID2, which is 2 milliamps minus 1 milliamp, or 1 milliamp. Okay. The other thing I wanted to solve for here was the voltage V out, and that, if we can see just through observation here, if both diodes are on, as I've represented with the pink bar through the diodes, pink short through the diodes, then the voltage here at V out is going to have a direct connection to ground, or is going to be at the same potential as ground, so V out is equal to 0 volts. Okay, so all of this makes sense. You know, nothing has been violated in terms of what we know about an ideal diode. Our currents are in the positive direction through the diode. There's no negative current, which we shouldn't have through a diode. The voltage drops across our diodes are positive. They're not negative. And we said they're on, so we would expect a positive voltage drop across an on diode. So again, nothing stands out as being an issue here. So let's look at a slightly different example. Let's just bring my circuit back in here. But let's call this example 2. The circuit looks the same, except I'm going to make this my 5K resistor this time, and I'm going to make this my 10K resistor. Okay, we still are going to have this point X and a voltage at that point called Vx. We'll have a current ID1, current ID2, a current Ix. Okay, so look very familiar so far. So let's make the same assumption as we did in the last case. Let's assume that both diodes are on. Oops. So again, assume both diodes are on or conducting. Okay, so again, I can take the voltage drop across R1, VR1. So I get, well, let me go here in pink and say, well, I'm assuming that both these are shorted. So I can, based on that, I'm assuming my voltage at this point is going to be 0. So that allows me to calculate this current ID2 which is the current through R1, is going to be VR1 divided by R1. VR1 has a drop of 10 volts across it again, if our assumption is correct. So 10 volts divided by 5K now says I have 2 milliamps flowing through diode D2. Okay, again, let's calculate IX. So just like we did in the previous case, IX, again, I'm assuming that everywhere along here is 0 volts because both diodes are on. And if that's the case, then I can calculate IX as the voltage across R2, right? So VR2 divided by R2, divided by R2 will give me my current through R2, which we've called IX. Okay, so 0 volts minus 10 volts minus 10 volts divided by R2. So this is 10 volts divided by 10K, which is 1 milliamp. KCL again here at node X says that ID1 plus ID2 should equal IX. So rearranging for ID1 equals IX minus ID2, and based on this I get 1 milliamp minus 2 milliamps, and this is equal to minus 1 milliamp. Now your first thought might be, well, this is fine. I can have negative current values, but I can't have negative current values through diodes, at least an ideal diode. So this is not possible. Right. A diode only conducts in the forward direction. Okay, so what's the consequences of this? Well, this is a indication that our initial assumption must have been wrong. Okay, so this means, so if we look, referring back up here to the top, right, what were these initial assumptions? We assumed that both diodes were conducting. Okay, so that assumption was wrong, because if it were a conducting or on diode, we wouldn't have current flowing in the negative direction as we found here. So let's try again, and this is kind of the approach with this analysis technique is trial and error. So another possibility that we can consider here is that diode D1 is off and D2 is on. Okay, so right away, so let's bring the diagram back in here. Oh, actually, maybe I don't have the diagram copied here now. Let me grab the diagram here again. Let's bring it back down here. Okay, so now we're saying that D1 is off. So rather than there being a short there, this connection is actually going to be open circuited. Okay, so there's no connection there. So right away we know one of our currents. We know our current through ID1, if we're assuming that it is off, means that that current is 0. Okay. Current ID2, we can calculate. So really, if that one is off, our circuit has been simplified to look like this. Okay, where this is D2, this is R1, which is 5K. This is R2, which is 10K. I can ignore this other branch here that was going to ground because this was open circuited anyway. Okay, so the current here that's flowing through D2, which we've assumed to be shorted, this current ID2 is the same current as IX now. Okay, so ID2 is going to be the voltage drop across both resistors. So we're going from plus, so I'm just going to take a total voltage drop. So a voltage, let me move this out here. Let's just call this voltage R from here to here. And so that's 10 volts minus a minus 10 volts divided by R1 plus R2, the two resistors, because they're both in series with that circuit, and I'm taking the voltage that's dropped across both resistors, which is a total drop of 20 volts across the total resistance of 15K, which indicates that my current is 1.33 milliamps, and I know that IX is equal to this same current now because there's no other path for current to flow. Let me relabel my voltages, my node on here. So this was point X, so voltage Vx is going to be the same as my voltage Vout. Right? If I'm assuming my diode is on, so I can calculate Vout as being equal to Vx. Again, this is because the potential is everywhere along this line showing in green here, if that diode is really on. So Vout is equal to Vx. Vx is going to be equal to the voltage across R2 divided by sorry, I can do this an easier way, or another way. Right? Let's talk about Vx as being minus 10 volts plus the drop here. So it's going to be plus this drop across VR2. Okay, so minus 10 volts plus the drop across VR2. This is 10 volts minus IX times R2, which is minus 10 volts. Oh, sorry, this should be a plus, right? Thus, we're going up in potential as I move this way away from 10 volts. plus 1.33 milliamps times 10 kilo ohms gives me a Vx, or a Vout, which is the same in this case, of 3.3 volts. Okay. Going back and looking at the original circuit, if this is equal to 3.3 volts, this makes sense that this diode would be off, because I've got a point of higher potential on the cathode of the diode, right? The voltage at this point, the cathode, is higher than at the anode, so that is consistent with a reverse bias diode. Okay, so this is consistent with D1 being off, since it's reverse biased. Okay, so just to summarize the process that we followed here, we start out by making an educated guess as to the state of each diode in the system. Right, so this is on or off, or off. And we do our analysis. Perform analysis, and then we check for contradictions like, and these are what would be what we don't expect, so this would indicate there is a problem. Contradictions or problems, let's say. This is might be negative current through a diode, for example, or positive voltage across a diode that we assumed was off. It shouldn't be what we expect, again assuming an ideal diode. Positive voltage across an off diode, or in the opposite case is negative voltage across an on diode. Okay, so if any of these occur, all right, these are things that we shouldn't see. So if this happens, then we'll make a new guess, if we want to call it that, and repeat. Okay, so that is an example of how we might analyze a circuit with diodes, assuming the diodes are ideal, and making an assumption about the state of each diode at the beginning of our analysis, and then checking for errors in our assumption. So we'll leave it off there. Next class we'll have a look at how real diodes compare to the ideal diodes that we've been discussing up till now.